Okay, so let's solve tutorial sheet 1, P191. And without wasting time, question 1 is saying, part A, the temperature difference between the inside and the outside of an automobile engine is 850 K. Express this temperature difference on a Fahrenheit scale. Express the temperature difference on a Fahrenheit scale. So this question is very simple. The only thing you have to remember is that the temperature difference in Kelvin is the same temperature difference in the degree Celsius scale. And in order for us to convert this temperature difference from Kelvin to Fahrenheit, we just say temperature in Fahrenheit, or I can put temperature difference in Fahrenheit, in degree Fahrenheit is equal to the temperature difference in Kelvin multiplied by a ratio of 9/5. So this will be equal to 850 Kelvin multiplied by 5/9. And this is going to give us a temperature difference, which is equal to 1530 degree Fahrenheit. Okay, so the temperature difference on a Fahrenheit scale is equal to 1530 or 1530 degrees Fahrenheit. So that's part A. Now let's look at part B, which is saying convert the following temperatures, -50 degrees Celsius to degree Fahrenheit, 450 Kelvin to degree Fahrenheit, and 200 degree Kelvin to degree Celsius. Okay, so that's part B, and this is also very simple. We already looked at how to convert different temperature scales from one temperature scale to another. So the first one is saying we convert -50 degrees Celsius to degree Fahrenheit, of which we said in order for us to convert from degree Fahrenheit to degree Celsius, we just say the temperature has been given in degree Celsius, which in this case is -50, multiplied by a ratio of 9/5 plus a constant of 32. And this is actually going to give us a temperature which is equal to -58 degrees Fahrenheit. -58 degrees Fahrenheit. Or degrees Fahrenheit rather, not Celsius again. This is degree Fahrenheit like this. Then part 2 is saying we convert 450 degrees or 450 Kelvin to degree Fahrenheit. So this is the same. And I said the middleman of the conversion between Fahrenheit and Kelvin is the degree Celsius. So firstly, you can convert your temperature into degree Celsius before you convert it into Fahrenheit. And what are you going to do? I'm going to say 450 Kelvin minus 273.15. That means we've converted this temperature into degree Celsius. Now let's convert it into Fahrenheit by using the same approach we used in part A of multiplying it by 9/5 plus a constant of 32. That means this guy in degree Fahrenheit will be equal to 350.33 degree Fahrenheit. That is part 2. Now let me create an extra space here for the third part of this question. Okay, so this one is going to convert 200K to degrees Celsius. And this one is the simplest because I'm just going to say 200K minus 273.15. And this is going to give us the temperature in degrees Celsius, which is equal to -73.15 degrees Celsius. And thus we are done with question 1. This is part A here, and this is part B, the first part, the second part, and the third part there. Okay, so let's move on to the next question, which is question 2. And question 2 is saying a thin spherical shell of silver has an inner radius of 1.5 times 10 to the power minus 2 meters when the temperature is 22 degrees Celsius. The shell is heated to 150 degrees Celsius. The coefficient of volume expansion of the spherical shell of silver is 57 times 10 to the power minus 6 per degree Celsius. What is the change in interior volume of the shell? What is the change in interior volume of the shell? So first things first, let's remember our formula for volume expansion. This is question 2A. And we say the formula for volume expansion, change in volume, is equal to beta multiplied by the initial volume multiplied by the change in temperature. And they've given us the inner radius, the initial inner radius, say R, to be equal to 1.5 times 10 to the power minus 2 meters. They've given us the initial temperature, which I'll call T0, to be equal to 22 degrees Celsius. They've given us the final temperature, which I'll call T final, to be equal to 150 degrees Celsius. And they've given us beta, which is the coefficient of volume expansion, to be equal to 57 times 10 to the power minus 6 per degree Celsius, like this. So what are we going to do? The first thing is we're going to calculate the interior volume of this sphere. So let's calculate the V0. And we know to say the volume of the sphere is equal to what? Is equal to 4 over 3 multiplied by pi multiplied by radius cubed, like that. So we're going to plug what we've been given into this formula, and we're going to end up with 4 over 3. I'll plug it the way it is, 4 over 3 multiplied by pi. I'll just punch pi on my calculator, multiplied by the radius, which is 1.5 times 10 to the power minus 2 meters, like this, cubic. Okay, and if I punch this into my calculator, I'm getting an initial volume, which is equal to 1.4 137 1.4137 times 10 to the power minus 5 cubic meters. So this is the initial volume of our sphere that we have. And now that we've calculated the initial volume, we can find the temperature change between the initial and the final temperatures, of which we're just going to subtract 22 from 150. That's going to give us, let's say, delta T will be equal to 150 minus 22. This is degrees Celsius, and that is going to give me 128 degrees Celsius as the temperature difference. So now we have the initial volume of our sphere, and we also have the change in temperature. So what are we going to do? Let's now calculate the change in volume of our metasphere, and we're going to use this same formula that we have here to say change in volume will be equal to the coefficient of volume expansion, which is in this case 57 times 10 to the power minus 6 per degree Celsius, multiplied by the initial volume, of which the initial volume is 1.4 times 10 to the power negative 5, multiplied by the change in temperature, which is 128 degrees Celsius. So the degree Celsius, which is here, and the per degree Celsius, which is on the coefficient of expansion, or rather, which is on the coefficient of expansion, this one, they're going to cancel out. That means I'm only remaining with the units of measurements, which are the cubic meter, which is on the initial volume here. Okay. That means my change in volume is going to be equal to what? It's going to be equal to 1.0306 times 10 to the power minus 7 cubic meters like this. Hence, we've calculated the change of the internal volume of our sphere. We're asked to say we should calculate the change in internal volume of the shell. And by so doing, we've calculated the change in internal volume of our shell. Okay, so that's a very important question to test your knowledge on your understanding of volume expansion and how to apply it in different scenarios. And we've managed to solve part A of question 2. Let's go to part B, and part B is saying the coefficient of volume expansion of a metal-sphere is 2.8 times 10 to the power negative 5 per degree Celsius. The internal diameter of the metal-sphere at 26 degrees Celsius is 4.5 centimeters. If the final diameter is 5.2 centimeters, what is the final temperature? What is the final temperature? Okay, another very, very, very interesting question. And here, what are we going to do? We're going to solve this question step by step. This is a very interesting question, by the way. But let's do it step by step. And by so doing, you can solve it in different styles or in different methods, but this is the one I'm going to follow. So I'm firstly going to convert the diameters that have been given into meters, from centimeters into meters. Then from there, we're going to divide them by 2 to find the radius. Then we're going to find the respective volumes of this metal sphere at the different temperatures that we've been given. And if we find the different volumes, we can find the change in volume, and we can put it into the formula of finding change in volume or thermal expansion of or volume expansion to find the change in temperature. Then we can add that change in temperature to the initial temperature in order for us to get the final temperature. So let's do this. This is now question 2B, which will be quite long. So question 2B, we've been given volume expansion coefficient to be equal to 2.8 times 10 to the power minus 5 per degree Celsius. And we've been given initial temperature T0 to be equal to 26 degrees Celsius. We've been given initial diameter, which I'm going to call D0, to be 4.5 centimeters. Then we have final diameter to be equal to 5.2 centimeters. So first things first, let's convert these diameters into meters by dividing them by 100. And I'm having this one as 0.045, this one as 0.052, like that. Then we can divide these guys by 2 in order for us to convert them from diameters into radii, or to their respective values of radius. And when I divide them, I'm getting here 0.0225 meters as radius. Remember, these are now meters. And then here I'm getting 0.026 meters as my final radius. Now that we have these guys, what are we going to do? Let's apply the formula for finding volume of a sphere in order for us to find the final volume at this point. I mean, the initial volume at this point, which we're going to call V0, and the final volume at this point when the radius was 0.026 meters, like that. So the formula for finding volume of a sphere is equal to 4/3 multiplied by pi multiplied by r to the power 3. And I'm going to use this exact formula to find the V initial, which will be equal to what? Which will be equal to 4/3 multiplied by pi multiplied by radius. And what radius are we talking about? It's 0.0225 meters to the power 3. The V final will be equal to 4 over 3 multiplied by pi multiplied by 0.026 meters to the power 3, like that. So that means our initial volume is 4.77 times 10 to the power minus 5 cubic meters, whilst the final volume is 7.36 times 10 to the power minus 5 cubic meters, like this. So we found the respective volumes at the initial and the final point. So let's find the difference now in these two volumes, which is going to give us the delta V, like this. And this is going to be equal to V final minus V initial, which will be equal to 7.36 times 10 to the power minus 5 minus 4.77 times 10 to the power minus 5. The units are cubic meters for both. I'll just put them down here. So if I subtract these two values of volume, the final and the initial volume, I'm getting a value of volume which is 0.0000259 cubic meters, which can simply be written as 2.59 times 10 to the power minus 5 cubic meters, like this. So this is the change in volume, the delta V. And we can now get this delta V that we have and plug it into this formula for volume expansion, which will be equal to that multiplied by the coefficient of volume expansion multiplied by V initial multiplied by the change in T. So our goal here is to calculate the delta T. So let's make delta T the subject of the formula. Delta T will be equal to delta V over the coefficient of volume expansion multiplied by volume initial. Now let's plug what we've calculated into this formula. So our delta T will be equal to the change in volume, which we just calculated as 0.000259 over 2.8 times 10 to the power minus 5. This is per degree Celsius multiplied by the initial volume. And what did we say the initial volume was? Said this is 4.77 times 10 to the power minus 5 cubic meters, like that. So we multiply the denominator, going to get our delta T is equal to 0.000259 over 1.337 times 10 to the power minus 9, like this. Okay, and if I divide these two, I'm getting a change in temperature, which is equal to 19 392 point. Okay, so I'll just say 0.0 like this. This is degree Celsius, like this. So now this is the change in temperature, and we know to say change in temperature is equal to T final minus T initial. And since we're looking at T final, we can make it the subject of the formula. So we're going to say T final will be equal to change in temperature plus T initial. And we're going to do exactly that, to say 19,392.0 plus 26. Therefore, we're going to get our final temperature T final as 19,418 degrees Celsius, like this. So You should take note of your decimal places, and this answer will vary actually based on the rounding off that you're going to do along the way to the final answer. But this is the correct way and method that you're supposed to use in order for you to find the final temperature, which is going to give you a diameter of 5.2 at the end of the day. Okay, so that's how you're going to solve question 2b. Question 2b, yes. And that means we're done with question 2. We can now move on to the last question, which is question 3. And question 3 is saying an aluminium plate has dimensions of 10 centimeters by 10 centimeters with a concentric circular hole of diameter 3.6 centimeters at initial temperature of 27 degrees Celsius. If heated to 100 degrees Celsius and aluminium's linear expansion coefficient is 2.4 by 10 to the power minus 5 per Kelvin, find 1, the new diameter of the hole, 2, the change in the area of the remaining material. Find the new diameter of the hole and the change in area of the remaining material. Okay, so this is also a very interesting question. This is question 3 now. Started on a fresh page. I'm going to say question 3 like that. We have been given T initial to be 27 degrees Celsius. We've been given T final to be equal to 100 degrees Celsius. We've been given the coefficient of area expansion, or first they've given us the dimensions. Say this is 10 by 10 centimeters, and we've also been given the diameter of the hole. So diameter of the hole is 3.6 centimeters like that. So what are we going to do? What are we going to do? They've also given us the coefficient of linear expansion alpha as 2.4 times 10 to the power minus 5 per Kelvin. Like this. So the first part, in order for us to calculate the new diameter, we know to say diameter is a one-dimensional expansion. So it's the same as we're dealing with linear expansion. So we're going to put this hybrid formula to say change in diameter will be equal to the coefficient of linear expansion multiplied by linear diameter multiplied by the change in temperature. So our new diameter will be equal to alpha, which is 2.4 times 10 to the power minus 4, or minus 5, sorry, the power minus 5 multiplied by the initial diameter, which is 3.6, multiplied by the change in temperature. So the change in temperature is 100 degrees Celsius minus the 27 degrees Celsius here. So we're going to say that is approximately 73 degrees Celsius. So that means our change in diameter, if I plug everything the way it is into my formula, I'm going to get a change in diameter which will be equal to 6.3072 times 10 to the power minus 3 centimeters. So this is the change in diameter. So in order for us to find the final diameter, like they asked us to say we should find the new diameter, what are we going to do? We're going to say change in diameter. Change in diameter will be equal to final diameter minus initial diameter. So the final diameter will be equal to change in diameter plus the initial diameter. This is going to give us this number that we found here, 6.3072 plus the initial diameter, which was 3.6. And this is going to give me my final diameter as 3.606 centimeters. My final diameter is 6.06 centimeters. So that's part A of this question. We've managed to find the new diameter or the final diameter of the aluminium plate. Now part B is saying we should calculate the change in the area of the remaining material, the change in the area of the remaining material. So the first thing we should do is find the initial total area of the whole or I can say we should find the initial total area and the whole area. Let's calculate the initial total area and the area of the whole. That's English there, just languages, and we should be able to deal with that. So this is part 2, which I'm going to call B, or rather just part 2, not B. This is part 2 of question A. So in order for us to find the change in the change in area of the remaining material, we're going to find the initial total area and the area of the whole. So total area of the square plate is going to be equal to what? It's going to be equal to the 10 by 10 dimension that were given in the first place. So this is going to be equal to what? It's 10 centimeters multiplied by 10 centimeters. So it is going to give us 100 square centimeters. So this is the initial total area. Then from here, let's find the area of the whole. Let's find the area of the whole. And for us to calculate the area of the whole, we know to say it's simply finding the circumference of the whole, which will be equal to pi r squared, like that. So the radius, since we are given the initial diameter, we can find the radius from that same diameter that we are given. So this will be equal to pi divided by 3.6, which was the initial diameter, divided by 2. Then I'll square this guy, and I'm going to get pi multiplied by the brackets. I'm going to have 1.8 squared outside, and this is going to give me an area which will be equal to 10.180 square centimeters. So this is the initial area of the whole. The initial area of the whole. So what will be the initial remaining area? The initial remaining area will be the total area, which is this one, minus the area of the whole that we have here. So this is going to be equal to 100 minus 10.18. The units are square centimeters since we're dealing with area. And this is going to give me 89.82 square centimeters, like that. 89.82 square centimeters, like this. So this is the initial total area. This is the initial area of the material. Since we've subtracted the area of the circular of the circular, let me see. Okay, yes, with we've subtracted the area of the concentric circular hole that is on the middle. Now that we have the initial total area, what are we going to do? We are going to use the formula for area expansion in order for us to find the new area of the material. So we're going to say change in area. Change in area will be equal to 2 multiplied by alpha multiplied by the initial area multiplied by the change in temperature. As simple as that. So we're going to say change in area, delta A will be equal to 2 multiplied by 2.4 times 10 times 10 to the power minus 5, like this. This multiplied by the initial area, which is 89.82, and this multiplied by the change in temperature, which is 73. Okay, so our change in area will be equal to, if I plug this into my calculator, I'm getting an answer which is equal to 0.316 square centimeters. 0.316 square centimeters. So that means with the change in diameter of the hole that we calculated, the change in the area of the remaining material is going to be 0.316 square centimeters. Okay, very important, and that is the change in area of the material that is remaining after subtracting the concentric circular hole that is on the middle, just like that. Okay, so let's now go to the last question, which is saying a circular disc has a concentric circular hole cut out of its middle as shown in the diagram. So this is the diagram. We have R1 as the total diameter of the whole material, and R0 has as the diameter of the concentric circular hole that is on the middle there. So suppose that R0 is 7.5 centimeters and R1 is 16.0 centimeters, and the coefficient of linear expansion is 3.2 by 10 to the power minus 6 per degree Celsius. What is the change in area of the material that makes up the disk for a 65 degrees Celsius increase in the temperature? Okay, some emphasis there because they've given us the change in temperature already. So let's go to the last question, which is question 3b. Question 3b, and we've been given the inner radius, I'll say inner radius, 7.5 centimeters, and the outer radius as 16.0 centimeters, like this. Then we have coefficient of linear expansion alpha as 3.2 times 10 to the power minus 6 per degree Celsius, like this. Temperature change, delta T, has already been given to us to say it's 65 degrees Celsius. So the first things first, let's find the initial area of the material. Let's find the initial area of the material, and we're going to use this formula. Initial area of the material will be equal to the difference between the area of the remaining material, or the area of the whole material, minus the area of the concentric hole, or the circular hole. So I can just say this is going to be equal to the area of the whole material, I can call 1, R1, minus the area of the concentric hole. So this is the same as pi open R1 squared minus R0 squared, like that. And this is going to give us what? This is going to give us pi multiplied by 16 squared minus 7.5 squared, like this. And this is going to give me pi multiplied by 256 minus 56.25. This is it in square centimeters now. This is we've squared the insides. And if I multiply this, I'm going to get the initial area A0 as 627.08 square centimeters. So this is the initial area of the outer material. If we've already subtracted the area of the concentric circle or the concentric circular hole from the area of the whole material. Now that we found the initial area of the material, let's use the formula for area expansion. Find the change in area. So the change in area will be given by 2 alpha, since we've been given alpha, multiplied by initial area multiplied by change in temperature. And this is going to be equal to 2 multiplied by 3.2 times 10 to the power minus 6, like this, multiplied by the initial area, which is 627.08, multiplied by the change in temperature, which is 65 degrees Celsius. Okay, so my change in area, my delta A will be equal to, okay, so if I punch everything at once, I'm getting something which is looking like 0.2609 square centimeters, of which we can just round this off to 0.261 square centimeters. So that means our change in area is 0.261 square centimeters. And ladies and gentlemen, when we reach that part, that means we are done with tutorial sheet 1. Please like this video, share, subscribe to the channel, and until next time, stay blessed.